The discussion on linear algebra, and what we have looked at is that the what is the condition for which we can find out a solution for Ax equals to b, and we have already talked about that b has to lie in the column space of A. That means the particular matrix A, if it is a order of m by n, then there is the column vectors, they will form a space, and assuming that there would be certain vectors which may not be independent, they are dependent, but even then, I mean, using the independent vectors, so there is a column space which exists there, and to have a solution for a particular system, the B has to lie in the column space. And then when you have that, then there are two components of the solution. One could be the solutions with the particular variables or the free variables, or one could be the pivot variables. And what we have looked at, when you do the elimination of the particular matrix or the linear system, so we get the row reduced form or echelon form, and from there we can identify the pivot variables, and then the solution will have two components, one come from the pivot components and one from the free variables. So, this is what we have looked at, and we even stopped here, and this is what, if you just recall that from the augmented system, the total solution vector, you will have pivot variable and you will have the free variable, and the column which corresponding to free variable, they will contribute to this solution, and finally the total solution would be of this kind of nature. So, this is coming from the pivot variable and these are the free variable, and for the free variable, this is going to giving a solution for the Ax(f0), which is so this guy is going to contribute for this one, which is the null space vector, and these are the basis vector, and any combination, these are C1 and C2 are the arbitrary scalar. So, any combination of that is going to form the null space vector. So, this is what we have looked at it. Now, even there are different conditions which may appear, and one has to deal with those conditions in a different way. For example, let us take certain cases, let us say case 1, where obviously the matrix is order of m by n, as we have said, and its rank is n. So, this is the rank, or whatever you call is pivotal rank. Okay. So, the number of free vectors or number of free variables. So, number of free variables, that would be n minus r, which is essentially 0, because this is so the solution would be only contributing from the pivot part, there is no free variable. So, this is not contributing anymore, that would be 0. So, what it means, the solution is going to be is or will be unique. So, this is quite important, that the solution that we get, that would be unique. So, we can see an example here, a quick example which can give you an idea, like you take an matrix like this, where it is a 1 3 2 1 6 1 5 1, and if you do the operations, so this guy is going to go down to 1 0 0 0 3 minus 5 minus 17 minus 14. So, what you have, the row reduced form is essentially I and F, and the solution is going to be unique. Now, that is particular situation where you have this case. Now, we can move to a situation where you have case 2, where again the matrix is order of m by n and your rank is now m. So, free variables would be n minus r, which is n minus m. Now, in this case there will always be a solution for B. So, that means there will always be a solution for B. Now, what you can see here, since the rank is equals to m or the exactly the number of rows, or you can call it as a row rank. So, as due to all row rank, so B vector will lie in the vector space. So, the way, if you take an example and reduce it, the row reduced form will look like that, because here you mind it, I mean you can take some example and look at it, but this is because of you have a complete row rank. So, the previous one, case 1, we have taken complete column rank or the pivotal rank, and next case is the row rank. Now, you can have a conditions where things are like your m into n and your rank is m equals to n, which is, that means this is a square matrix. So, this is when r equals to m equals to n, one can say this is either full column rank or full row rank. So, either of them are fine, you can say it is a, so the whole, both of them are here. Now, so which means the A is completely invertible, and thus only one solution exists for Ax equals to B, which means my row reduced form will have this. So, only one solution exists for this. So, when you have full rank, either full column rank or row rank, this is what it is going to happen. And there could be another situation where you can have for A equals to m by n, either r could be less than m and r is less than n. So, this will be the rank, which is neither full row rank not full column rank. So, if you just have the row reduced form, so they will look like this, and this is the kind of cases what we have been already taking some example and looking at it. So, here what will happen in this situation, either zero solution or there would be infinite solution for Ax equals to B. So, these are the two possibilities which may occur or appear here. So, when you see this kind of situation, so that brings to an important issue of that, and all what we are saying here, the solution of Ax equals to B, and then we are talking about B has to lie in column space and they consist of some column vectors, and the vectors have to be independent. So, that is where we bring the formal definition of linear independence. So, essentially when do we call a set of vectors to be linearly independent? So, let us say there are set of vectors which are x1, x2 to xn, and basically if none of the vector is a linear combination of the other. So, what we are saying that none of the vectors are linear combination of other. So, which is not necessarily all of the other, then the vectors are linearly independent. So, which we have been also looking at the column space vector. If all the columns are not kind of any of the column is not a linear combination of the other columns, then all the columns are independent and we can get full pivotal rank, which would be the case for like situation where r equals to n, like that. So, in mathematically what we can write? We can write for any scalar C1 x1 plus Cn xn, where this is possible for linear independence if and only if all Ci are 0. So, then what we can say that all the xi vector are linearly independent. Okay. So, there is no linear combination in order to find another in case of a linearly independent set of vectors. Okay. Now, the thing when there is a span of a vector space or basis and dimension. Okay. So, here again when you try to explain that, we will start with an example. For example, let us say 1 1 1 1 2 1. So, this would be 2 3 2. So, this corresponds to x1, this is x2, let us say x3. Now, here there are 3 vectors and they are spanning over 3 dimensional space. Okay. Now, any addition, scalar multiplication does not cause change from a 3 dimensional space. Now, that is one situation. The other case, in this column vectors, what you see here, if you see carefully, these two if we add it, then the third one we can get, or from third one to subtract the second one we can get the first one, or third one to first one we can get this, which clearly means the 2 column vectors, any 2 column vectors, they are linearly independent, not the third one. So, the column space will have 2 independent vectors, and this is an 2 dimensional subspace in R3. Okay. So, this is an 2 dimensional subspace in R3. Now, the conditions of being basis vectors. So, there are conditions of being basis vectors. One, they are linearly independent. 2, they span over the space. So, these are the conditions for being basis vectors. So, here what we have, the x1 and x2. So, this would be basically let us say x1 and x2 are the basis vectors here, x1 and x2 are basis vectors. So, x3 would be dependent. So, the number of basis vectors, when you get the, so the number of these basis vectors give the dimension of vector space. Same thing here, because we said that column space has two dimensional subspace, and because the two vectors which are going to be linearly independent. Now, here for this particular example, this A, which is 1 1 1 1 2 1 2 3 2, the rank is 2. So, that means that many pivot variable or pivot columns are there. Okay. So, for a linear system, the rank denotes the dimension of the vector space. So, that means for, this is very important to note, for linear system, rank denotes the dimension of vector space. So, once we find out that rank, which means there are number of pivots or the pivot columns or whatever it is. So, when we find out that, that define the vector space or rather column space. Now, similarly, we can find out the number of vectors in null space, which is going to basically give us the 0 solution for a linear system. Na would be n minus r, which is 3 minus 2 1 for this particular example. Now, here the basis vector for the null space would be, one can clearly see that, because just to, we have already discussed these things, how to find out the null space basis vector. We can do that Ax equals to 0 solution. From there we can find out the null space basis vector. But since the example that we have taken here looks quite simple, through visualization one can say the basis vector here, the basis vector here is 1 1 minus 1, because if these two are considered to be independent, then the third one is going to give us the 0 solution. So, and the solution would be alpha into 1 1 minus 1, where alpha goes between minus 2 plus infinity. Here there is only one basis vector, and any other combinations with alpha or C1, whatever the scalar, this could form the null space here. Null space forms a 1D subspace, because the number of basis vector is going to form the vector space. So, here the number of basis vector is 1, and we can have multiple solutions with any scalar multiplying that, because for example, alpha you can take minus 1, then this would be minus 1 plus 1. That means, from here if you minus these two, this is going to be 0, but the basis vector does not change. So, this is the basis vector, and there is any scalar which can give you infinite number of solutions, but since there are only one basis vector which represent the 0 solution to that, this forms a one dimensional subspace. And this is very important, how these column vectors in a linear system contribute to all these different spaces. whether column space or null space or column space. Now, we can with that we can actually go to a like we look at the fundamental subspaces of. So, we go to the fundamental subspace of any linear system A. So, we look at what are those. So, we have already looked at that, like there are 4 fundamental subspace, one would be column space, one would be null space, then you can have column space of A transpose, null space of A transpose. Okay. So, we can see just taken 3 by 4 system, let us take an system. So, the idea here is that when you take an example, you can easily visualize what is happening here, and then through that you can come to an solution quite quickly. Now, here as we say, so the any system for linear system of m by n, the column space belongs to R to the power m, okay, and the null space would belong to R to the power n. So, now for this particular example, here the column space would belong to R to the power 3 and null space would belong to R to the power 4. Okay. Now, what happens to row space of A, which is equivalent to column space of A transport? That means, if I have a system, if I just do the transport, that becomes the row space of A. In this particular case, the A transport would be 1 1 2 1, 1 2 3 1, 1 1 2 1, which is 4 by 3, which means the column space of A transpose belongs to R 4, and that saying that column space of any n by m system, that column space of A transport belongs to R to the power n. Similarly, here if you look at the left null space, which is the null space of A transpose. So, this belongs to R to the power m. So, if we put these guys in sort of an kind of a picture, here this would be my column space of A transpose, null space of A. So, this is in R n, or if I see that, so this is column space of A, null space of A transpose, that belongs to R to the power n. So, this is the picture what you can see when you talk about these fundamental subspaces. Now, another thing, important thing is that the dimension of ME matrix is given by its rank R, and let us say R is less than M or less than equals to M or N. So, that is a possible. So, for any this M by N system, if the rank is R, the number of free variables would be always N minus R. Okay. So, let us take this guy and look at these different fundamental subspaces. So, we have 1 1 1, 1 2 1, 2 3 2, 1 1 1. So, what we need to do, again do the elementary operations, let us say R2 minus R1 and R3 minus R1. So, what we get is that 1 1 2 1, 0 1 1 0, 0 0 0 0. So, there are pivots here. So, R would be 2 because there are 2 pivot variables. So, the dimension of the column space would be rank, and that would be 2, and the number of rows which is also independent. So, the number of rows which is independent equals to 2. Again, rank of A and A transpose is same. So, that would be 2, and hence the rank of A transpose. So, the rank, hence the rank of A transpose is number of independent rows. Okay. So, the column space of A transpose also has a dimension equals to 2. Okay. So, here the number of free variables would be should be n minus r, which is the dimension of the null space. So, now one can find out the dimensions of these fundamental spaces. For column space, this would be the rank, and column space of A transpose, that is also R. Now, the dimension of in A or the null space, which is the number of free variable, which is n minus r, and dimension of the left null space or A transpose, which would be m minus r. So, these are the 4 fundamental subspace and their dimension, what one can find it out. Now, here if we do little bit of more operation like R1 equals to R1 minus R2, and what we can get here is that 1 0 1 1, 0 1 1 0, 0 0 0 0. So, which is saying equivalent to the row reduced form, and that is nothing but IF00. This is corresponding to free variables, this is independent variables or pivot variables. Now, column space of matrix and the row reduced form are not same, as even though row operations are done, columns are being changed. So, that is very important to note. Hence, basis vectors are being changed. Thus, so what we are trying to say here is the column space of a matrix and the row reduced form of not the same, as even though we have done the row operations, but columns are being changed. So, the basis vectors are being changed. So, the column space of A is not the same as row reduced form column space of row reduced form. So, here because basis vectors get changed, hence the span also changes. So, this is quite important to note that this would happen when we do that. Okay. So, now in this particular case, so what we can say that a m into n is I n into a m into m, which is row reduced m into n elementary m into m. So, now here if you look at the E m into m into a m into n equals to reduced form of m into n. If R is I, then E is A inverse. Now, the point here is that how to find basis vector of null space of A transpose. So, that is the questions which raises here. So, we will stop the discussion here and continue from here in the next session.